So I would just, my job only is actually to say you should get started. I pass on actually to Bob Kowalski. I think Bob doesn't need much of an introduction as the godfather of logic programming, and gave a great speech last year at our conference on how that's happening and how that's working. And we still have the video. We post the video again and again. So for everybody who would like to listen to that presentation of last year, we'll make it available again. But I would hand over to Bob and this panel, and I hope you enjoy it.
All right. Hello, everybody. I'm not Bob Kowalski. Bob will be hopefully with us shortly to introduce the panel. And but given that he's evidently have some interconnection problems, so I'm going to just jump right in and start with my presentation. I'm Michael Genesereth from Stanford. I'm the first of several panelists that Bob has lined up to talk about logic programming in the legal context. So I'm going to kick things off with some discussion, general discussion about computational law. Share my screen here with you, or my keynote presentation here with you, so that we can have some things to look at. Right, so hopefully you folks can all see these slides. It begins and says computational law, the cop in the back seat. All right, computational law is often defined as a branch of legal informatics having to do with the mechanization of legal reasoning. And this possibility of automated legal reasoning has obvious implications for the legal industry, rather substantial implications. But more broadly, it has implications for society at large, everybody, not just legal professionals. And today I want to talk a little bit about computational law in general, and then, but specifically to focus on the second potential, namely the implications of computational law for everybody, not just legal professionals. So let me make my case, or begin my case, motivate my case by a little hypothetical scenario. So imagine you're in another country when it all opens up again on business of some sort, and you get up in your hotel, have your breakfast, and you're off for your day's activities. You're driving down the street. You can't see any signs. You don't know what the speed limit is. How do you know how fast you can go? Are you allowed to make right turns on red in this country? Can you use your cell phone while driving in this country? Can you make a U-turn on this street? Okay, back in your hotel after your day's activities, you decide to spend some time working on personal chores. Can you buy those drugs from that Canadian pharmacy? Can you ship that wine to your aunt in another country? Looking at maybe taking care of your healthcare provisions, or those for example, for your grandparents. Does your insurance policy cover in-home care, or does she have to go to a nursing home? These are questions for which the law and contracts we form have answers, but we don't always know those answers without pouring through lots of documents, and in many cases having to get legal help. The fact is that we live in a world with a wide variety of regulations. In the United States, regulations come from federal government, state governments, local governments. And in addition, we form contracts with each other that further regulates what we're allowed to do or what we must do. And the result of this is that, first of all, there's an enormous number and size of regulations. And we may all agree on some general standards. They may be very small, but the specifics of how those standards are implemented as rules can be more complicated. In the United States, an important document is the Declaration of Independence, which sets forth the principles on which the government was formed. That's 1,322 words. But if you look at the regulations on the sale of cabbages, there's 26,900 words. And it's not bad writing. It's necessary because when you take general principles and try to deal with all the special cases, and then we need to say more about how the general standards apply in those cases. It's not just size, it's not just number of regulations, but it's also complexity. This is a couple of quotes from my homeowner's policy. On page 32, it says, my insurance coverage includes water damage, which made me very happy the day that water came in my house from a broken water main in the street. Unfortunately, when I tried to get my damage covered, I discovered that I hadn't read page 112, which says that the coverage on page 32 does not apply to damage caused by floodwater. So it seems contradictory, and if I only read part of it, I would have trouble. So the problem with this is we have many regulations, we have complex regulations, and so there's often lack of compliance with these regulations. There's inefficiency, and many times there's a widespread disenchantment with the legal system. Okay, well, I'm a computer scientist, an information theorist. And for me, this is an information processing problem. And my belief is that legal technology should be able to solve this problem. And as this conference and others have made clear, there's already a significant amount of technology that can address this. Textual representations of the law online have been the norm for some time. Books are online in the United States, cases, statutes, secondary sources, analysis of the cases, and so forth are all available. And you can search for them in Google and a variety of specialized search tools that take advantage of key phrases and pagination and markup and so forth. And there's quite a bit of work on this that takes place. Some people in this very conference are working on these problems. So that makes for good legal text search. You want to find the laws or the cases that apply. You can find them by using these search tools, and you get some documents, hopefully the relevant documents to the particular situation at hand. But the problem is you still have to read the documents and you have to understand the documents. A better situation is made possible by computational law. Again, the branch of legal informatics concerned with the mechanization of legal analysis. We don't just want the text of the laws in our computers. We want the ability for the computer to do legal analysis. We want answers to our questions, not just documents. And so computational law really addresses this aspect of legal technology, and hopefully as we see it beginning to happen. For example, in the United States, there's a system called TurboTax. I don't know what the equivalent is in other countries. Maybe it applies there as well. But millions of people, tens of millions of people use this to prepare their taxes each year. It's a great example of computational law. The laws are embedded in the program in computational form. You enter your data about what you earned each year, and it tells you exactly what you have to pay, taking into account all of the tax code about deductions and expenses and so on and so forth. Some of the systems actually can give you explanations as to why this number is the way it is. Some other extensions allow you to plan ahead so that you can take certain deductions in 1 year to save taxes and so forth. So TurboTax is an example of such a system, but it's not just limited to tax code. There are lots of others as well. So let me give you an example here of a slightly different system. This is a prototype produced recently by a company called Symbium, which shows computational law in the case of building codes and planning codes. So the idea here is if you're trying to build a new house or put a new building on your plot, is it legal? Is the size legal? Where can you place it on your lot? So this is a little tool that allows one to look at one's proposed design. Here it's just a schematic of a building, and you can look around and we can move this around, and you'll see that if you move it in the wrong direction, too far in one direction, then some things, it turns red and some X's appear. What's wrong with that is that there's a setback here, setback restriction here, and you can find out why. You can find out why that setback restriction is the way it is, or you can make it taller. Oops, sorry, let's move it so that it's back here. I think I can do it so it's fine, but now it's too tall, or maybe it's too large. And so this is a good way of interactively finding out what you can do. And what's happening is the code for the program, the building codes are embedded in the system in a way that integrates all of that information, setbacks, shadow lines, and so forth, and makes it available to the user in a consumable form, an understandable form, way that he can relate to. Okay, so let me rush back here to this system, to this presentation. Okay, so that's another example, but they're not alone. There's quite a few, not just Intuit and Symbium, but there's comp law systems out there to manage childcare after divorce, visa applications, Form Ally, Co-Inspect for doing building inspections, AXA, a large insurance company that's concerned with doing computational form, laws in computational form. And if you want to find out more, you go to techindex.law.stanford.edu, 1,350 companies there, of which several dozen are doing directly what I would call here computational law. So there's quite a bit of activity in this space. All right, so what I want to do is talk about two things. One is, how do you make them, build these systems? And two, what's the implications of building them? All right, so first of all, the answer to how to build them is very clear. You go back a little bit to a seminal document in this field from 1986, written by none other than our chairman, who may not be able to see this at the moment, but there's his name on the document. And it tells us that the answer is logic programming. And today, still, 30-some years later, this is still probably the best technology for building comp law systems and is used in many of the ones I just mentioned. So logic programming gives you a language to define concepts, like what does it mean to be an office mate? These are examples from a corporate policy handbook. But same technique would be used for governmental rules. So here you can define concepts like what does it mean to be an office mate? You can define legality and illegality. You can't both be in the same, manager and a subordinate can't be in the same office. And so one can write these definitions formally, not just in natural language, but in a formal language, which makes very precise exactly what the regulation, what the policy says. The reason that logic programming is so good is that declarative semantics. You say what's true, not what to do. It doesn't talk about what you're going to do with this information. You merely state what you believe to be the case. What is that definition? And although some people in the logic programming community may disagree with this, it also can be done in a way that's independent of the interpreter. It doesn't matter how you're going to process. Different interpreters can apply to it because the semantics is separate from the interpreter and from the task. Okay, so the benefit of this is it's easier to learn how to do logic programs. It's easier to write and read than traditional programs. It's like if you think of spreadsheets and how easy it is to build to program quote unquote spreadsheets. That's closer to what you can do in logic programming than what you would do with Java, writing Java code, for example. And arguably, it could constitute a new legalese a new standard for writing laws that are computable. Okay, well, if you just were writing them, that would be one thing, but you can also then use these rules and regulations written in this form because interpreters do exist. Take a traditional logic programming interpreter like Prolog, you can apply it to formulas like the ones I just mentioned to you to produce answers. Okay, this is illegal because John and Ken are in the same office and John manages Ken. You can use a different interpreter for different purposes, to plan things based on the constraints that are available, or to analyze constraints. To say that in general, it's true that these constraints are illegal or are incompatible with each other. Different interpreters, same exact rules and regulations. Okay, so that's logic programming. You also, because the rules and regulations are independent of their use and the task, one can share them with each other and combine them in ways that's not possible with traditional programs. Put those programs inside of tools for building user interfaces and thus deploy apps, legal apps like the ones I showed you earlier, the Symbian app or something like the Intuit app, the TurboTax app, and then make them available via the internet, via mobile devices, in our cars, maybe even someday on autonomous robots. Okay, so now we have these apps embodying the legal code made available to everybody in society, not just sitting in the office. Not in the legal office. So what are the implications? Here is the implication. On to my second of my 2 points, the cop in the back seat. Law is now available to you everywhere you go, can be made available to you everywhere to go, to advise you what you can do, what you can't do. This is a bit of an antiquated concept. When I developed this slide 15 years ago, this was actually a new idea. Your speedometer should not just say how fast you're going, but maybe should have a little line on there that says how fast you're allowed to go. And maybe even other things like how fast other people go. What's the average? It can give you more information about what's legal and what's not legal, as well as what's the case situation in the world. This has been in cockpits in airplanes for a long time. Those little blue lines say where you can fly at what altitudes. The cops should certainly be on the internet to tell you whether you can buy those Canadian drugs I mentioned, or whether you can send that wine to your aunt, as I suggested. And it could even be in nature. You take a picture of that flower with your cell phone and you have your app that identifies the flower, but the other app that tells you you're allowed to pick it or not. In the United States, if you're in one state, you can pick it. If you're in another state, you cross over the border, suddenly you're illegal. Where you are determines whether you can pick the flower or not. So comp law technology allows us to get law out there to where it's being used when somebody's about to do something, not after the fact when you're in court. So that's the basic idea. Let's get it out there for everybody to use using this basic technology. There's a broader implication here, which is, I began my talk by saying how standards can be expressed very succinctly, but the rules are complicated. And the rules have to be complicated because when you go through all of the details of how to sell cabbages, you need to cover all those various different cases and issues. But so complexity is important. It's essential. In fact, it's important for efficient operation of society. But its harm is that we don't understand the rules and regulations, and we violate them, or we don't know what they are. We spend a lot of time understanding them. But comp law allows us to reap the benefits of complexity without the cost of that complexity, without the cost of understanding what we're allowed to do and what we're not allowed to do. That's one of the benefits of it. It makes the system more efficient and makes our lives a little bit easier. Let's see. So, but there's a broader issue here, which is comp law democratizes the law. It gets it out of the law office, out of the courtrooms, and into the hands of people when they're making decisions, when they're trying to decide whether they can do something or not, when it tells them what they're allowed to do, what they must do. It allows them to know what their rights are and to achieve those rights from the government or from insurance companies or whatever else it is. The idea is to help the individuals, not the lawyers. We also want to help the lawyers, but we also can help individuals who are not legally trained via this kind of technology. Okay, well, anyway, so that's my basic point. Let me just finish by saying that Hammurabi was the start of the legal technology, in my view, was the start of the legal technology field when he carved his code in stone back in 1750 or something like that BC. And since then, there have been innovations, the printing press, the internet, which allows us to take the code and propagate it to everybody so everybody can read the rules. But the problem is that the rules are so voluminous and so complex that we can't understand them, then the purpose of the code and the laws is lost. But if one can produce tools that can implement them and make them available to decision makers when they're about to act, then we can solve that problem more easily. So in some sense, it's the next step, maybe the ultimate step in the evolution of legal technology that began millennia ago with Hammurabi. And today is hopefully will produce a legal system that's more efficient and a better system than we've had in the past. Anyway, that's my set of remarks for you. Thank you for listening.
Thank you a lot for having me. I hope you can see this application. I tried to make it available. So my talk is, in a sense, also a repetition of what Michael just said, maybe using a slightly different perspective, namely the perspective from the actual administration. So I work for the Austrian government in the Department of E-Government for Businesses in the Austrian Federal Ministry for Digital and Economic Affairs. And all these regulations that Michael mentioned are especially prevalent, of course, within the administration itself, because there are countless actual cases where we need logical reasoning in the administration. So I just give a few examples here. So typical rules are of the form, because you run a business of some type, you are subject to certain laws, or because you are replying or not replying within a deadline, some consequences. Because you're a citizen of some country, of Austria, for example, some specialized laws hold. Or just the speed limit that Michael also mentioned, of course, this is a typical example that arises in the administration, or because you're studying, you are eligible for certain grants or situations. So these are all rules, logical rules that arise in the administration, and it's no coincidence that we can easily write these things as logical rules, because in fact, in Austria, it's in fact a constitutional principle that all administrative acts must be rooted in laws. So in fact, the administration can't make any steps that are not written in laws. It's all explicitly available already. And these are exactly the things that must be carried out by the administration. And there's a deep motivation behind this principle, namely the administration must behave predictably, and more than predictably, one could say even computably in modern terms. So it must be perfectly clear in a sense what the administration will do. So this will, to remove all the shadow of bias, this should be clear to every citizen. It must be completely predictable and computable what the administration will do. Of course, to the greatest extent possible, at least. So this also means that decisions of the administration must be explainable, traceable, and justifiable. This is the ideal situation. So to avoid any bias, some things that would be considered unfair. So this also means that especially symbolic AI methods are of particular relevance within the administration, because in the administration, the challenge is not to guess the laws from available data. So it's not the case that we are looking at the data and then try to fit some laws by statistical methods to best approximate the available data. That's not the case. The laws are already perfectly known. So the challenge in the administration is to automate reasoning about laws. So, and Michael already mentioned a few very interesting examples. For example, if I did something, would that be still lawful? Or other cases, for example, ideally, we should be able to reason about the laws and ask for automated simplification of laws, if possible. Or even in a more futuristic case, try to propose certain laws that could make sense or could benefit the entire situation. So increasingly futuristic applications. But certainly, in the ideal case, law should certainly be automatically executable. And in fact, we already have various projects to formulate laws exactly as logic programs, because as Michael said also, logic programming is simply an ideal formalism to reason about logical rules. And in fact, we are already starting some prototype projects, such as eligibility requirements for grants, proof of identity, certainly, which in effect also is a logical rule involving also cryptographic principles, where we make sure that some person really has an established and guaranteed proven identity. Also affecting delegation of powers, which would be an example of a smart contract. Also cross-border use cases, especially, of course, within the European Union, and also queries about laws. So, and one thing, it's also clear that we need better methods to implement such IT services, because what we're currently doing already stretches the limits of what these languages can provide. And logic programming, as mentioned, is really truly an ideal fit for this huge overarching team, Codex as Code, which also coincidentally, I mean, it's no coincidence that codex and code have the same Latin word root. Codex, meaning a trunk of a tree, that as soon as it became available, readily, of course, replaced scrolls. So, and of course, we're already providing certain IT services. And in fact, especially Austria is in many areas a leading e-government provider. We have many dedicated services for citizens, for businesses, providing, for example, e-delivery, e-procurement. So these are all already available services, and also tax administration, which is also mentioned, is of course already available as an IT service in Austria. But currently, the gap between the codex and the code is too large. So these are currently almost completely separate entities, even though they should be the same. So ideally, the code should be derived from the codex directly. And for example, for text law, it's also, at least in some cases, or some paragraphs at least, are already written in a form that could be very easily made automatically executable if we apply the right formalism, so the right programming language. And there's more. I mean, currently we are also limited by the technologies that are being used, because in the end, an IT service provided by the government should not be only just some fixed application, but an application that is extensible and customizable by clients, by citizens, by businesses, and allow also flexible rules that can be stated and formulated by the clients. So for example, regarding e-delivery, a citizen could say, if I'm on holiday, then I want to be notified differently. For example, then I want to receive a text message in addition to an email, or then if I'm on holidays, a neighbor may also sign some delivery, or my attorney shall automatically receive a copy, for example, of certain deliveries. So for instance, if some certain amount of money is involved, then my attorney shall automatically receive a copy. So, and also not only between citizen and businesses and administrations, but also between businesses, we should provide a platform, for example, so that businesses find each other if they have similar interests, or so that clients can find sellers and so on. So this is also an example of smart contracts where businesses could establish cooperation on an intelligent, extensible platform. Also regarding data analysis projects, for example, if two businesses want to cooperate, also involving maybe research, universities that play also a role. So these are examples where we need also extensible platforms. And of course, we are, especially in Austria, of course, we are embedded in a European context. So we are a member state of the European Union. And there are various projects also initiated by the European Commission that are closely related to these issues. So logic programming will certainly play a role also in a European context, because also here the Commission always tries to ensure provability, trustworthiness, traceability of decisions. This is a really important strategic goal in the European context, and also part of national AI strategies that are being developed. So the more this focus on reliability and traceability increases, the more it will become evident that we need really mechanisms that are closely related to logic and logic programming. Just to pick one of these examples is the single digital gateway. So there is a regulation already in effect. So this is written law, the single digital gateway regulation, with the goal to enable cross-border use cases. So for instance, a Spanish company should be able to create a branch in Austria, and should ideally be able to provide country-specific evidences to our administration that we can automatically prove as valid. So this may, for example, involve querying registries, or uploading documents, or asking the citizen or business owner for some things. So ideally, in this case, we need really executable descriptions of what's needed. And these descriptions should be really not only machine readable, but machine executable. So for instance, to prove that in Austria, for example, to prove that you are born in a certain location, there are various registries available that we could query, and this could be a logical rule of the form that if some e-government service needs this information, then in Austria it's established in this form. In Spain, it could be established in a different way. In some other country, in yet a third form. But no matter the specific way in which these evidences are proven, the formalism should be the same for all countries and be compatible between countries. So also here we see this important question of standardization of this formalism, so that we can in fact interact. So I think it's evident and clear that technical standards for these rules will play a very important role in the future, the more we want to cooperate also in cross-border use cases. And also, especially in a small country, like a relatively small country like Austria, technical standards for such formalisms are also an important, in fact, an important benefit for businesses that want to sell such IT solutions to other countries, because this is where, how our companies are very export-oriented and sell such IT solutions also to other countries. So technical standards here benefit cooperation in the European context. So. And that's not the only, of course, these are not the only advantages of standards. I mean, even to teach such formalisms, for example, it starts really with the teaching. We need technical standards to even know what these formalisms mean, to teach them in universities, to teach them within the administration, to simplify procurement. Also, when we need IT solutions, we need technical standards for this. And also to mitigate legal disputes, of course. So there are many cases in the administration where some software didn't work as advertised. So we need a strong way to enforce changes by the vendor, and this is made possible if there is a strong foundation, technical foundation, and a standard that really outlines how these formalisms interact. And this is also what Michael mentioned. It's clear, of course, you can take a logic program and run it in different interpreters. And for Prolog specifically, there is an ISO standard. And as long as you program within this standard subset of Prolog, then the expectation is that we can really switch Prolog vendors easily and run the same program with the same result in a different implementation. And if a vendor doesn't conform to the standard, then we have a strong legal argument and can have a much stronger position if the vendor advertised compliance to the standard, but in fact isn't compliant. You are in a much stronger position as the buyer of the software than with a system that behaves randomly or doesn't conform to the standard. So also within the administration, of course, this is really a solid foundation of cooperation between different governmental institutions, different countries. So this is a strong and important case for standards. And for this reason, I also represent the ministry in several standardization groups that are currently becoming increasingly relevant. For example, there is an ISO subcommittee 42 on artificial intelligence with many experts, with over 20 countries already involved, with the entire subcommittee, so almost more than 150 members participate in the plenary meetings. There is also a dedicated subcommittee and a working group 17 for Prolog. So subcommittee 22 is programming languages and their environments within ISO. Working group 17 is Prolog, dedicated, has also a long history and a long tradition, and has produced a nice technical standard for the language that's still being worked on. And also there are dedicated standardization efforts for blockchain technology. So these standardization efforts are really the way how we ensure that we have a solid foundation for cooperation, and how we make how we establish a good situation for our, especially of course Austrian companies, so that they can actually port the solutions, sell their Prolog compilers, for example, all over the world, because the standard is international. And here we also have many opportunities for cooperation. So this is, if you're interested in these technologies, then the ISO standardization efforts is really one of the best ways to establish contacts with international experts of these technologies. And also I have included this rather technical slide about an actual Prolog system that's now emergent, because Prolog is, of course, a language with a long tradition, and yet it takes a certain amount of time, at least, to really manifest the full potential of the language. And only now there are implementations becoming available that truly unleash the full power of Prolog. For example, by providing very fast and efficient implementation techniques, or by really incorporating the latest declarative results and the latest semantic concepts that are now established in universities. So this is just one example of a Prolog system that's currently becoming available. It's very interesting, and that we are also considering to implement various pilot projects in the Austrian administration. And this I would like to ask you and invite you for cooperation. And so if you have any comments about this, or any questions or experiences, project proposals and so on, or are interested in standardization efforts, please let me know anytime. I've included here my email address. I think that these technologies will become increasingly relevant in the future, because we are interested, and citizens and our businesses also expect increasingly complex and increasingly sophisticated IT applications. And to provide them, we really need powerful technologies, so that we can really implement these solutions faster, more reliable, and with better semantic properties, so that they can really reason about the solutions we implement, also make them available as under free licenses, so that we can enforce cooperation, ensure cooperation between citizens, businesses, and the government, so that we can work together. So this will be an increasing opportunity also for companies that are interested in legal tech and logic programming to establish strong alliances between themselves, between the administration and interested citizens. So with this, I would like to close and hand back.
Well, here we go then. Right. Well, I'm Miguel, and I'm coming to you live from Lisbon, sort of. Okay, so this is going to be quite a little bit of a lower level talk after what can I say? I started reading Michael Genesereth's papers in mid-80s. I've used Markus Triska crypto libraries in recent years, and I won't even mention Bob. So I'm really honored to be with you guys on this one. But again, this is kind of a practical log, practical with double quotes, over the last maybe two or 3 years with Bob and Fariba Sadri at Imperial College London. We've been looking at using an extension of logic programming to smart contracts or executable contracts in general. So first, I'm going to very quickly skim over a particular extension to vanilla logic programming, something called logic production systems, which Bob and Fariba came up with about a decade ago. And then I will look into a few very small examples of smart contracts from literature, if you will, and see how we look at them, and then try to come up with some sensible conclusions. Now, you've all, of course, at least everybody in the panel, if not in the audience, is familiar with logic programming to some sense. So logic production systems can be seen as a kind of rather simple and neat, in my own biased opinion, extension to basic logic programming. And so, whereas in some system like Prolog and derivatives, you look at a predicate like bits, scissors, paper, meaning that for all time it's true that scissors is a better play than paper, say in the rock paper scissors game. Other predicates require use of time, and so there are events, things like there was a transaction with certain attributes from time 1 to time 2, or there's an event I meant, or there's an action, meaning that the system, the logical, the contract, if you will, the logic program did perform some action like making a payment maybe on a blockchain from time 2 to time 3, and also there are fluents. Fluents meaning meaning the traditional designation for logical predicates that evolve over time for some good reason. So, for example, at a certain point in time, say at time 2, maybe the reward available for a game is 2,000, but that, of course, will be true at time 2 and not before, not after. Well, maybe later, but not before. Maybe G2 for game over at 3. So, and you can see here slight nuances on syntax which are not really relevant. The slides should be online by now or soon by the organization, or you can contact me later. So in order to get back to this or follow the links, etc. So I'll just move on. Very brief. Well, not really a footnote. I've been using logic programming on and off, since the mid-80s, and I must say that over the last 2 decades, I find Swish, which is an interactive web environment for Prolog, to be maybe the most significant system development, which allows people to experiment with logic programming and deploy it in rather user-friendly and flexible ways. And so this is just my love letter to Swish. And let me move on. The reason, of course, is that our own system is, in terms of user interface, uses Swish. It specializes or customizes Swish. So I thought I should mention that. Now, first example is going back to, well, arguably the inventor of the concept of smart contracts, Nick Zabel. He did write a little technical note maybe 20 years ago or so, which is online here, and proposing a kind of a contract language, a formal, well, not so formal, but a kind of a formal language for representing legal contracts. And he gives several examples. The first one, which is a kind of a minimalistic example, is this one, and I'll try, and let's see if I don't bungle this entirely. Hold on. Let me see if I can. Okay, hopefully you'll be able to see. I hope you see a large O and some code. Anybody sees it? Yeah. I'll yeah. Thank you. Okay, so here on the left, well, there's a lot of comments, with the original contract specification on his language, etc. But I'll jump right into this. So the idea that this contract is really a very trivial, very simple contract. It's a futures contract in the sense that two parties make the decision to promise each other that they will swap something in the future. And that something in this case is one round lot of pork bellies, and that will be exchanged against $1,500, and that should occur, within some date interval. And so the contract is really just this. I mean, the main clause, the single clause of the contract is this. It says that, well, for a futures contract to be honored, given some rights to an asset A and some right to an asset B, the future contracts will be honored if at some time t, at the same precise t, the two parties, holder and counterparty as they're named here, they will exchange possession of this to things, to items, cash and a lot of pork bellies, whatever that may mean. So this is really just a traditional implication. It's a simple. It's really a horn clause, a prologish horn clause, except that there are times which you can look at as in practical terms as extra arguments to the predicate. And then there's something else. There's this, we call it, or Bob and Fariba called it, a reactive rule. And in this case, it's a rather weird one, but it says that, well, it must be true that this thing is true. So this contract must be true, meaning that, given a particular set of events, I'll just simulate two events here, okay? And if there was a transfer of $1,500 and there was this transfer of the pork bellies, then the contract succeeds. But if you meet one of those, let's say that this guy did not pay for the pork bellies, then of course the contract fails. Now this not, well, this does not sound like rocket science, and it isn't, but hopefully it will show that logical truth here corresponds to a contract being honored or being, you know, compliant with reality, and if the logic program does not have a model, if it fails, then, you know, then the reality does not comply to the contract. Okay, so this will just get you into the spirit of this. Let me go back to the slide, if I may, if I can. Okay, right, so we were here. Okay, so next example. This is, you know, a rather typical clause for late delivery. You know, whenever someone sells something to someone else, usually there may be, you know, a penalty clause in case there's a delay in delivery. And this is grabbed from, you know, nice folks at the Accord project, which is, you know, a large project concerning also with executable contracts and all that. And this is our take on it. So you can see here on the left, I'll go to the right one in a minute. On the left, you can see that, well, if there is a change of date, you know, there's going to be an increase in the penalty if these conditions hold. So this is really just, you know, yet another ORM-like clause, a simple implication, but, you know, there's just some little details about arguments and you know, and some semantics attached to it. And this is what, you know, we call a kind of a post condition. That is, it's a kind of a rule which stipulates how state should change over time. On the right, you can see something that, well, mostly Bob has been working on for a while, which is which we call logical English, which is really just a kind of a, well, two things. It's a kind of a syntactic sugar for logic programs, but it's also intended to be as a pseudo-natural language dialect, so that precise pieces of contracts can be written. So the idea is that the text on the right and the logic program on the left, I mean, on this clause here, are equivalent. You know, hopefully that may, you know, the right side of the slide hopefully will be more appealing to you know, to non-logic programmers. So another example, third example. Now a little game. You know, we flirted with a couple of blockchain systems over the last couple of years. One of them was Tezos, and you know, which is just one. I would say after Ethereum, arguably might be the most interesting smart contracts platform. Well, maybe if you write off Hyperledger, so I would say one of the top 3 most interesting ones. And this is, you know, just a simple example where there's a player that tries to guess a number, and then the system generates a random number, and depending on you know, the bet, the number that the player did bet, and the random number, there will be a prize or not. So on the right, you can see the precise specification in logical English. On the left, you can see the working code in our system. And you know, later if you follow this, you know, you can go to the website and run it as I did with the other one. I will not do that now in order to save time. So just just a couple of comments on the code here, on the logic program on the left. So first, at the very end, notice this in line 26 and later. If a player tries to guess a number n, and if the player does bet with some cash in the value of bet, then what the system should do is, well, pick a number and then apply the rules of the game, and then either perform an action stating that the player has lost the bet, or on the contrary, compute some price and make a payment. Now, as you may have guessed by now, the colors in the predicates on the left on this piece of on this little logic program here, the colors are important. So the orange predicates are events or actions, and the blue or gray, whatever you feel like it, these are fluents. So you can see here that if an event of a play occurs, then eventually there's going to be an action telling the player that he has lost, or that on the contrary he has won a prize. And also there are here prohibitions or integrity constraints in database parlance, but prohibitions in legalese. So it's forbidden to play, to bet, to bet a number which is not between 0 and 100, for example, on line 17 and others. You cannot have two plays at the same time and other things like that. Moving on. This is a slightly more elaborate example. Well, also a toy example, but interesting in that it can be used to put things working together. Later, and I think I'll try to move forward and avoid wasting time now. So I invite you later to come back here and try. There's a video showing this working on Ethereum. You can try this with simulated time, without the blockchain. But the idea of rock, paper, scissors, there's, it's a game that I hope most of you know. So there's some timeless logic at the top, stating which are the gaining moves in relative terms. And if you scroll down here to maybe line 27, you can see what does it mean to pay a prize. To pay a prize, you do this and then do that. And these things, these predicates, which do have rather technical names, which don't sound user-friendly at all. These are in fact system predicates to manipulate the Ethereum blockchain. So, but finally, maybe popping up to a higher level, the last two clauses, the last two reactive rules are, state the rules of the game, saying basically that, well, on line 32, I mean, if one player played something, the other played something else, and if one choice is better than the other, then eventually pay the price to player 0. And further down below, it's the case for draw when the prize is split between the two players. If you follow this, we'll not do this now, but there's a short video, maybe a couple of minutes, with a demo showing this working on an Ethereum testnet.
Excuse me, Miguel,
yeah.
We're running out of time.
We're running out of time. Yeah, was that the message? Okay, right. So one last example. One last example is is a simplified loan agreement by Flood and Goodenough. Well, I will not. I don't have time to show it here, but again, you can, well, actually, I will just try very briefly to direct you to it. It should be probably around here. My system is a little bit unresponsive. So, if you follow that link, you'll eventually come up here and you'll find a notebook that, explains our version, that actually Bob did most of this, I should say. And you can either see the behavior of the contract over time as you did before, by simulating payments and requests from the borrower and the lender, or you could also see a different visualization of the contract history by aggregating predicate fluents and kind of extracting or aggregating states. You can see the same thing in a more traditional state diagram with state transitions, which some people may find interesting to look at. So finally, just a quick slide on the implementations of this logic program extension, LPS. And with respect to conclusions, well, I wouldn't. Well, I don't really have very high-level conclusions other than the obvious that by having looked at smart contracts for rather superficially, to be honest, but we've looked enough to realize that they involve traditional software engineering problems, AI representation problems. There's a strong case for readability, and that's how we came up with the logical English idea. And there are practical issues which I'll omit for now. And finally, we are of course very interested in doing collaboration projects of all sorts. Everything you saw is open source. The links in the slides will let you have. Will guide you to Bitbucket repositories, etc. So everything is open source and can be used without any strings attached. And that's about it.
Well, thank you very much, Miguel. I very much hope that effort is. I think education today is very deficient in matters concerning how to think clearly, as we can see in a number of different domains. So, Michael, that was you. If I may, I'm going to try to now introduce Markus. Is this working all right? Let's see.
Has not advanced.
Okay, can you see?
Yes.
So now, okay, great. So we're making progress here. So Markus, as you already know, is working for the Austrian Federal Ministry for Digital and Economic Affairs. He completed his PhD in Vienna, and he is one of the main contributors to SWI Prolog, which Miguel is so fond of. But he too is an author. He's written a book which is these days the most popular and most well-cited book. You can see if you do a search for Prolog books in Hackers News, you'll see that the three most highly cited books on Prolog now are Markus' book. And so if you're looking for an expert to educate you about Prolog and its applications to legal reasoning and applications in government affairs, then Markus is your man. And then we have Miguel, who you also have heard. He also did his PhD, but this time in Lisbon. And his PhD goes back to logic programming of the explainable variety, because debugging involves explanation. And he too is a a serial entrepreneur who has founded a number of different companies, some of which, the last one of which, Coherent Knowledge Systems, is still very active in the States. He has had and still continues to have academic associations with a number of Portuguese universities, and was past president of the Portuguese AI Association, as well as a member of one of the Prolog standardization groups. And as you know, and as he said, he has helped us developing LPS, and we have published a nice paper concerning our implementation of that in Swish. Well, this would have been an introduction, but it's probably not a bad time to introduce logic programming in relation to alternative approaches in particular. So you might well ask, if logic programming is so great, why isn't everyone using it? Well, the answer, more or less, is because there are so many other alternatives. And one of those alternatives, the one which is possibly most popular, is the use of imperative programming languages, which have their own kind of conditional logic, which I put in quotes, because that logic has an imperative element. Perhaps we'll have more to say about that a bit later. And in particular, the conditional logic that you find in imperative programming languages involves an element of condition action rules, an element of if certain conditions hold, then perform certain actions. And there are languages, expert system languages in particular, where all knowledge is expressed in this condition action rule form. And arguably, although they still have an imperative character, arguably they are more logical, although in fact their logic is some sort of imperative logic, which is not very clear. On the other hand, among real logicians, among classical logicians, among people who have, especially people who have studied, well, either philosophical or mathematical logic, you have other logics, such as those called Deontic Logics, which are specifically designed to deal with obligations, prohibitions, and permissions. And you haven't heard much about them in this workshop today, but they have a very long tradition of being one of the favored approaches to the representation of legal documents and legal norms in particular. Now, anyone who's looked in the least at legal texts will know that legal rules are full of exceptions. And the treatment of rules and exceptions in any kind of logic has been quite a challenge over many decades. And logic programming was one of the first approaches to this problem, but other so-called defeasible logics have also been developed, many of which have much of the flavor of logic programming and can sometimes be hard to distinguish from them. On the other hand, if you focus on smart contracts, for example, and look at the languages that are being used to implement smart contracts on blockchain systems, for instance, you'll see that there are basically no logical languages being used for that purpose whatsoever. And among the more advanced languages being proposed and being developed are functional programming languages, and they're contrasted with the more imperative programming languages, which are being characterized as not as declarative, shall we say. So these functional programming languages applied to smart contracts are often described as being declarative. And of course, we have logic programs. Now, if you look at Wikipedia and you type logic programming, you'll find, or if you had typed, for example, rule-based system, you'll be redirected to logic programming. And what this shows that there's a tremendous amount of confusion to this very day between logic programs and rules in other systems, such as condition action rules, event condition action rules, reactive rules of the kind we have, for example, in LPS. And again, Wikipedia describes logic programming in these terms, and I don't need to dwell on it because you've already seen it. This would have been a nice, hopefully nice introduction, but you can see that Prolog is not the only logic programming language. These days, answer set programming is a more popular alternative among logic programmers, at least. And Datalog, which is a database variant of logic programming, is also quite popular in its own way. I don't want to say too much about conditional logic, except LPS has got a kind of conditional logic, which LPS gives a logic to, but imperative languages have conditional logic, which isn't a real logic and which doesn't have a real semantics of a kind we would recognize as being logical. I don't want to monopolize the discussion time. I hope I'm close to finishing. I think what we need to do is compare logic programs with the alternatives. We need to compare them with functional languages. We need to compare them with imperative languages. We need to compare them with Deontic logics and defeasible logics. And we need to convince ourselves that we're on the right track when we're proposing logic programs as an appropriate representation. And this is just one example. If you look at rules and exceptions, it can be quite natural to represent them, for example, by saying that the rule holds if that a conclusion holds if certain conditions hold, but then to contradict that statement in a sense by saying the rule doesn't really hold unless some restrictions hold as well. And in conventional simple logic programming, we translate that into a much simplified form where we say the conclusion holds if conditions and restrictions. So this is just one example of the kind of comparison and understanding we need of the relationship between logic programming and other competitive or competing approaches, and to convince ourselves whether we're really capable of representing the kinds of knowledge needed for legal and other applications. We need to do the same with Deontic Logics, and I won't take any more time to look at that. We need to do the same with functional programming, and this is perhaps the most mysterious competitor, because functional programs are being sold for smart contract applications, and many smart contract languages are written in functional programming languages such as Coq, Camel, Haskell, or Lang. And their great selling point is that they're a stepping stone to formal specification and verification. On the other hand, some of us have sold logic programs as not needing verification because they are simply executable specifications. Okay, we can now, I think, go to our discussion. So I have a number of questions for our group. If logic programming is so well suited for legal applications, then why isn't everybody using it? Are logic programming representations really self-verifying, or are we deluding ourselves? What do functional programmers mean when they say functional programs facilitate specification and verification, especially if we claim that you don't need to verify logic programs because they're already specifications, executable specifications in the first place? Are existing logic programming implementations good enough for legal applications? What about legal rule ML? Is legal rule ML the way forward? And is legal rule ML a form of logic programming? Is controlled natural language a syntactic sugar for logic programming the answer to all our problems? Or should we translate uncontrolled natural language legal text into logic programming? Would that be a good idea or not? And don't let me forget that we have to hand over at the end of our little discussion to the conference chair. So that was me looking at my slides, and I now invite our little group to pick a question and maybe give an opinion. Michael, you're a presenter. Can we start with you?
How about I was the first presenter, and so I will start. And I wanted to take a crack at.
Well, you're senior in more than.
Second, please. I didn't hear what you said.
Carry on.
Okay.
Just as well.
Okay. Let's see. So I want to take a crack at what might be the first question, but also to ask a question of Markus, who made a very compelling case for standardization and the importance of standardization. But the issue I wanted to raise is whether it is sufficient, not whether it is necessary. And if it's not sufficient, that might also explain why LP is not being used more. So the issue I wanted to raise is that in building up, by the way, I see LP being used in many applications. It actually is a wonderful way of capturing the logic of laws and contracts. The problem is not that logic. The problem is the words that we use. We find that the so-called ontologies that people use in writing their logic programs may differ from one person to another. One person uses one particular set of terms and symbols and relations, and another one uses different ones. And this vast variety of ontologies does inhibit the fulfillment of the logic of the ideal of logic programming in the legal context. One of the things we found in doing many of our works is it's hard to decide how to describe the world, and when we do it, other people use it a different way. And if the ontology doesn't match the data that's available, then you can't apply the logic programming to anything. There's no data to apply it to because the data is over here in one language, or maybe it's even not even structured. And yet we have this beautiful logic programming, but we can't apply it to the data because the data's not structured, or alternatively, there's a mismatch. So the issue is, where's the effort on standardizing the ontologies, or at least talking about how we can mediate between different ontologies? In my view, that's stopping us from realizing the declarative ideal, as a result of which we go off and build all these siloed systems. Anyway, that's my challenge to Markus is, where's that aspect of standardization taking place?
Okay, so thank you.
Markus, do you want to reply?
Yes, certainly. This is a very, of course, justified question. And also, I mean, a prologue, and maybe I can also incorporate this specific question that arises here in the chat by Matthias Hudobnik, who says, where is the real advantage of prologue? So I think these issues are related a bit because, for example, I see many prologue applications. So to me, this is definitely a very practical paradigm. And one major attraction I see about prologue is that there is a timeless aspect to it. So I know that this syntax, starting just from the syntax, this will always be there. Just as logic will always be there as a formalism to automate reasoning. So prologue, in a sense, gives me some relief because I know in 50 or 100 years or 200 years, this will be the syntax that's used to denote a program. Whereas with many other languages, they come and go very, very fast and quickly. So in the other languages that I mentioned here, I mean, in 10 years, maybe they're still used in some dialect or in some form, but they will maybe look rather different or stop existing being used. Whereas this first order logic will always be here. So, here the issues of standardization also come into place. Just consider for a long time in the ISO standard, it was uncertain whether prologue syntax can even be standardized because you have flexible operators in the language, and these may also conflict with just to give one example, with the notation of floating point numbers, where you use an exponent as e, which could conflict with an dedicated operator. So these are just on this specific syntactic aspect. It wasn't at all clear whether the language could even be standardized from a syntactic perspective. So, and these are the issues we certainly must address first to really get, before we even come to semantics, we really have to address these basic syntactic things. And even today, not all systems are conforming to the ISO standard, but this is certainly a necessary aspect for further steps. So I think there cannot be any doubt doubt whatsoever that standardization is a necessary aspect to teach these languages, to cooperate in a meaningful way, and to use it as a building block then for more profound and maybe more high-level concepts, such as specific dedicated semantics, higher-level language constructs. And here, in my personal opinion, the field is wide open. So there are many language constructs in Prolog that are not yet found, that I believe exist, and that will be found in the future to make the language more powerful, more expressive, and then also to ease more applications and these semantic questions. So that's at least my personal opinion. And regarding these, also the time scale that we're looking at, these are very, I think these are projects that we are, as humans also, are not yet used to from a timing perspective. So this will take many decades still to fully develop. So these are the timescales on which complex software projects happen, on decades.
Okay, can we address another question from Ruta about hybrid logic programming, let's say, with natural language processing, and this also addresses the last two of my questions about either controlled natural language as a syntactic sugar, or translation from uncontrolled legal language in particular. Would these be desirable or possible, or would one, are they alternatives that we can say one is better, more feasible than the other? Miguel, I know we've had debates about this in the past. I wonder if you could give me your current thoughts about this matter.
Actually, I was just typing a response. I just typed a response in the chat. So for machine learning and logic programming, or intersection thereof, I would direct people to Fabrizio Raguzzi's work and system. I just put a link in the chat. The CP-linked system, which is a kind of a kitchen sink approach. I mean, it covers tons of algorithms and aspects of machine learning and in intersection with logic programming. Introducing probabilities and many other things. So I would simply suggest that people go there. As for natural language processing, as I wrote in the chat, we will be having a little extension to use the Space parser. Space is a well-known Python-based dependency parser, and we happen to be using it in a project recently. And so we have some code that we will release into open source in a few weeks, so that logic programmers in Swiss or outside Swiss, doesn't matter, but Prolog programmers can easily write logic programs that also invoke all the power of a full dependency parser. For English or for a number of maybe 6 or 7 languages. That's it. But just another comment, if I may, or to wrap my comment. So as as most of the people in the panel know, dealing with natural language and translating into some formal representation, whatever the domain is, and legal contracts being a specific instance of that problem, is really non-trivial. So I bow to your experience, Bob, as you've been advocating for several years now, that rather than going that route, it's maybe more productive to encode contracts in a let's say stripped down or formalized subset of English, and that seems to be a lower hanging fruit as opposed to looking at an existing contract and trying to extract its logic straightforwardly, which is very, very difficult to do.
Okay, we're running out of time. It's been an interesting and helpful discussion. I the last word by saying my experience of looking at legal contracts and for example, the ISDA, International Swaps and Derivatives Association, Master Agreement and Schedules. My experience is that lawyers don't write logically. They often write something they don't mean. They don't use parallel syntax for parallel semantics. So there's a lot that lawyers could learn from logic, never mind logic programming. And so a controlled natural language would be useful for legal applications, whether they're executed by computer or not, I would propose. Now, we do have to finish. I want to thank the participants who asked questions which we didn't have time to address, but thank you, everyone, and apologies for problems with my presentation. And over to the stage where we're having a final session, a final goodbye. So thank you, everyone.